E6. Love it. Love it. Let's take a look at it. All right, we're recording. Let's take a look at the vote. So we got a vote for E6 and E7. What is the percent error for each experimental probability? Give one way the errors are similar to the ones in E3. So I'm going to have to go back to E3. Yeah. All right, so, what the hell? Let's go back to the beginning here. Look back to exercise 1 on page 368. All right, hang on a second, friends. Let me, while we're here, let me get that out. Worksheet. Here we go. Larson text. We need, I forget what we need now. We need exercise 1 on page 368. All right, so here's Larson. How do you guys feel about the open source online text? What do you think? Good?
Really nice.
Would anybody prefer to have a, oh my goodness. Would anybody prefer to have a, oh wow, what is that? That's cool. Sorry, my ADD's kicking in. A print version of this with the print versions? You saw the links on the Heroes page.
Yeah,
You can order one, right? Okay, good. I mean, it's too late. I wouldn't do it now, obviously.
I just click over on there and then just go through the page.
Oh, gotcha. Then you can print them that way too, right, for sure. Okay, so here we go. Exercise 1, a dodecahedron die. That's one of these guys here. Dodeca. Isn't that cool? Cool word. 2, do, 10, deca, together 12. Very, very cool. 12 sides. Number 1 through 12. You roll a dodecahedron. Exercise 1 through 6. Find the probability of the event. Rolling a 6. But what's the chance of rolling a 6? It's 1 out of 12. Why is it 1 out of 12?
Because it's 12 possibilities.
So let's just we'll add this to the board over here. This is text number 1. Okay, so we have the probability of rolling a 6 is 1 in 12. Okay, so there are 12 sides, one of which is a 6. Tell me about those 12 sides. Why it's 1 in 12? Why is it? Tell me about those 12 sides. There's an important couple of words that I want you to make sure you associate with those 12 sides. Even if you don't verbalize them, I think you might be thinking about them, but at the same time, I want to give you an example as to why I want to make sure I drive this point home. Ben, what am I talking about?
The equal probability.
Right. There is one way to roll a 6, and there are 12 equally likely outcomes. One of which is a 6. So that's when you talk about that kind of classical probability where you're analyzing outcomes, you want to make sure that, at least in your mind, you know that. And here's why I bring this up. Yesterday in 243, we were analyzing a problem that I dealt with about 2 years ago now. It's about 2 years ago. We bought chicks. I'll see some of you guys in 243 at some point. Maybe not. But one of the problems I like to analyze is what's the chance if I send my son into a feed store on April 1st and I say go buy four little marshmallow peeps, put them in a box, bring them home, make a chicken flock. What's the chance they're all girls? And what people will often say is, well, that's like flipping a coin. It either is a girl or it's not a girl. Each little marshmallow peep you pick up is either a girl or it's not a girl. So there's 2 outcomes, correct?
Right.
It's either a girl or it's not a girl. Are they equally likely? That's the difference, is they're not equally likely. When you're buying pullets, which are called female chicks, when you're buying a pullet at a feed store, it's been sexed. The little bird that he picks up is 90% girl and 10% boy. Now I say that. I'm talking about averaging. They're 90% accurate when they sex them. So you're looking at this big, huge tub of pullets. 90% of those pullets are actually female. The other 10% are roosters that got missexed. Does that make sense? Missexed. So there are 2 outcomes. It's either a girl or it's boy, but it's not equally likely. So you can't say when Max goes in there to grab a chick, it's 50-50 that he got a girl. It's 90-10 that he got a girl. You see what I'm getting at there? So that's the difference between rolling a die like this and, well, actually, we could simulate that experiment using a 10-sided die, couldn't we? 10-sided die. Imagine a 10-sided die. This is 12-sided, right? So imagine a 10-sided die where 9 of the 10 sides had a little G on them, and one of the 10 sides had a little B on it. And that would be like Max going in and grabbing a pullet. rolling that die,
Yeah.
right? Because he'd roll it, and there's a 90% chance that he's going to get a G. There are still 10 sides, but now 9 equally likely of the 10 are G's, and one's the boy. So I bring that up only to make sure you guys keep that in the back of your mind when you think about probability. When you step, I think I've used this one with you guys before. When I get on my bike to ride home, I may or may not encounter opposition from a car driver. That doesn't mean it's 50-50, right? It means I either will or I won't. The chance that I will is very, very small, but it's a possibility. So I can't say it's 1 and 2. Yeah, there are 2 outcomes, but those 2 outcomes are not equally likely outcomes. Does that make sense? Based on my anecdotal evidence, I've got about a 1 in 10,000 shot of dealing with some kind of a cranky driver on my commutes. Which is pretty good. That's pretty good. I've got more chance of breaking my leg falling in the snow than having a nasty encounter with a driver on the way home. Fair? Okay, good. So now we got that. Let's go back to the homework page now. About 8%, there we go. Let's make sure what that means. Which of the following 2 statements is true? Is 1 and false? Boom, here we go. Here's E1 and E2. What do you think? Which one is true? Which one is false? Tell me why. Tell me why.
Like what you just said, the first one's false.
For what I just said, what did I just say? I said a lot of things. I talked about young bucks getting squirted with fish, water bottles. Say that again.
Equally likely.
Okay, so if they're equally likely, then I should go to roll 12 times and get a 6
It's
in there.
not average.
Ah,
On average.
on average, I should get a 6 every 12 rolls, which I believe is what E2 is saying, is it not? Over time, you will get 6 on 1/12 of the rolls you roll. That does not say roll 12 times and guarantee a 6. That means if I look at a long run of, you know what, let's simulate this right now. Everybody grab the TIs. I don't have any 12-sided die, but you do. You do. Get your TIs. We're going to simulate this bad boy. Everybody, take your TIs. We're going to simulate this right now. No, not free screen. Want to blink? No, I don't want to blink. Bring it up, man. All right, you ready? Here's what we're going to do. We're all going to roll a dodecahedron die. So, math, PRB, rand between, excuse me, that's Excel. Rand int. Rand int, number 5, I think on mine.
Okay.
1, comma,
Where's comma?
right above 7,
Comma?
12, comma, 12. What this will do is this will roll a dodecahedron die 12 times. The 1 and the 12 give it the limits of what it should roll, and the last 12 says do it 12 times. Everybody ready?
Wait, do it.
Press enter.
Press enter.
You are now seeing the results of those 12 rolls. Let's scroll through it right now, friends. Let's scroll through it. And you scroll through it by using your right arrow key to see. I myself got no 6s. I myself. Now you got 1.
I got one.
You got 1 over there. Okay. I got none. I got a bunch of 5s, it looks like. Maybe a couple 1s and 3s.
I got one.
Okay, I got some 10s, yeah. So here's what I want. Oh, Scott, what you got? 2 6s. Okay. So here's what the 1 and 12 means. I got no 6s, but Scott got 2, which means together we averaged 1 together. See? 2 over 12. Excuse me, 2 over 24. Not necessarily 1 over 12, but 2 over 24. Over here, I saw John also got 2, which means somebody else who didn't get any gets to share with John, and they average 1 per 12 as well. Cindy, did you get any?
No.
No 6s for Cindy, so John and Cindy share. See what we're getting at here, friends? You know what? Let's do this real quick. What I want to do is, I want to collect some data here real quick. I can hold this down so you can see how I'm doing. This is the kind of stuff we do in 243 on a daily basis. Oops. I must have pushed something I didn't. I'm going to go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops. 10, 11, and 12. How many of us got no 6s at all on that trial right there? No 6s at all. That's me. 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 9. Beautiful. How many of us got 1 6 on those trials right there? 1 6 on those trials right there.
Oh, wait, no, I lied.
That's okay, you can lie. That's quite all right. 1, 2, 3, 4, 5. Oh, I kept myself. Guys, we're going to try to count. 1 6 again. I'm sorry. 1, 2, 3, 4. I was counting. Oh, 5. Matt, that was 5. Good.
Can you add me to the 0 6?
Yes. Of course. How many got 2? I know at least 2 of you got 2. 3 of us? 3 of us got 2. 3 of us got 2. All right. Anybody get 3 6s? We got a few 3 6s? Yes. You see what's happening, friends? How about 4 6s? Anybody get above 4? Okay, these are all zeros. I'm going to zero these bad boys out. Okay, so what I'm going to do, and I hope we have time to do this in this class. We'll see if time permits. I'm going to run the average of this on L5 and L6. Oops. Forgot to put a comma. All right. Right there. Our average was 0.85. What is 1? We got 85% of a 6. Now, on average, we should get 1 out of 6. That is damn close to 1. That is damn close to 1. It rounds to 1. If you rounded it to the nearest whole number, it would be 1. And that's what that means. It means on average, we're getting that 1 6 out of 12 we should be getting. That's what this and I hope we have time in this class to talk about statistics a little bit. Maybe the very last thing we do, talking about statistics up here. So that's what I'm looking at. It's not that it doesn't guarantee us after every 12 trials where a 6 is going to show up. I'd actually be really surprised. Did anybody roll all 12 and get exactly 1 of each of the 12 numbers? Do it again. Do it again. So run that.
You can talk through the steps again.
Well, actually, all you got to do is press second enter.
I never got in there.
Second. Oh, okay. Well, just hang tight, Cheryl. Yes.
So I was curious, why is the number supposed to be 1 on top?
Because you did 12. We all did 12 rolls.
Yeah, but once you take it, went to be 1 divided by 12, and then you.
That would be the probability, not the number. It's the average number of 6s that we saw. Great question, Jake. It's the average number that we saw. Everybody do it again. How many people in this room got 1 of each of the 12 numbers? Well, I'm out because I got 2 4s right there. And once again, did I not get any 6s? Once again, I got no 6s and a whole buttload of 10s. Pretty slick.
No 2.
Right. Anybody get all 12 numbers? Amazingly hard for that to happen. Amazingly hard. And the more numbers you have on the die, the harder it's going to be to do it. A two-sided coin, it wouldn't be surprising, would it? It wouldn't be surprising, oh, it's a two-sided coin. You flip once, you get heads, you flip another time, you get tails. There's a 1 in 2 chance of getting 1 of each. But as you start increasing the number of sides on the coin, it's much, much more tricky. It's much, much more tricky. And this is a 12-sided coin, essentially. Fair enough? So I think we're happy. With the answer to the first question. This E1 is fictitious. It's fictitious. It is not a promise that you will get a 6 every 12 rolls. It's that you will average a 6 on every 12 rolls. Every 1/12. 1/12 will be 6s, 1/12 will be 10s, 1/12 will be 11s, 1/12 will be 4s, and so forth and so on and so forth and so on. Is that fair?
Yeah.
Believable. Okay, good. Calculate the percent error of each of the experimental probabilities. That's poor grammar. I appreciate that. Should be no period and lowercase f. 371 exercise 25, which would be there they are. Compare the probabilities you found in exercises 23 and 24. I am like the king of go back and look at this, to go look at something else, to go look at that, and eventually fall asleep and need more coffee. Okay, so, okay, here we go. Experiment, okay, I love it. So we're doing the same thing we did in class with rolling dice. No, we didn't. We were rolling dice, but we're pulling cards out of a deck. So here's a poker deck of cards. Any of you guys ever do something called a deck of doom? It's a CrossFit workout where you pick 4 exercises and you assign 1 exercise to each of the 4 suits. So you might do well, dice work too, but this is more bastardly, because like say you do push-ups as diamonds, crunches as clubs. We have these things called burpees. We'll call those hearts, and we got these things called fat kid Joshes that are spades. And what is you shuffle the deck, and you pull a card out, and the suit tells you what to do, and the rank tells you how many to do. So an ace could be 1, but we usually call an ace actually above a king. So we go 2, 3, 4, 5, 6, 10, 11, 12, 13. Ace would be 14. One time I drew a near royal flush on pull-ups.
Oh, God.
And my partners were all like, son of a bitch, what is the chance? I'm like, pretty good. It's pretty good. I mean, we had 4 of the 5, and they're like, they were sitting there doing like 52 pull-ups in like a minute and a half. I'm like, just shut up and do them. It's gonna happen eventually. It just happened to be today. Anyway, so number 23, theoretical probability of choosing a card of each suit. What's the probability of choosing a card of each suit? Suit being diamonds or spades or hearts or clubs. Ben?
A quarter rounded fourth.
Exactly, a quarter, a fourth, 25%, however, 0.25, however you want to write it. The theoretical probability is 25%. 25%, that's theoretical classical, and you know that because there are 4 suits in the deck. Okay, so this is 23. 23, the theoretical is 1/4. Okay, now 24 asks us to do the experimental probability for each suit, and that's what we've got down here. Okay, so this is similar to what we did in class last time. We knew the theoretical probability of rolling a 1 or a 2, it was always 1 in 6. The theoretical probability of a dodecahedron die is 1 in 12. But the what's that? Dodecahedron. It's a fun word. The empirical or experimental probability doesn't make any assumption about the equal likelihood of the outcomes. It just says, let's just do the experiment and see what happens. So for 24, let's look at each of the outcomes. We've got 17 hearts, 8 diamonds, 13 spades, and 12 clubs. So let's do that as an outcome and see what the probabilities are.
Yeah.
Well, you didn't get that? What is the probability? It's color coding too because we can. What's the chance of hearts, friends? Let's be fancy and draw a picture. Oh, yes. Go ahead. Oh, nice. What's the what's the chance of hearts? Experimental probability. 17 out of how many did we do altogether? Looks like 50. Yeah, I see 25, 17 plus 8 is 25, 13 plus 12 is 25, that's 50 altogether. 17 out of 50? What's that as a percentage? Yes, you do. Yes, you do. Look, yes, you do. You ready? If it's out of 50, double both and it's out of 100. Right? If it's out of 50, just double them both and it's out of 100. So it's 34%. Yeah? Fair?
Yeah.
Okay. What is the probability of yes! 8 occurrences out of 50, which is 16%. That's how many diamonds we got. So 8 out of the 50 correlates 16%. Fair? Tell me if it's not fair. Tell me if it's not fair.
All's fair, love and war.
So this is not love nor war, this is mathematics. It might feel like war sometimes.
War.
Yes. Okay. Let's do the probability of spades. Okay. We got 13 out of 50, which is 26%. 26%. Okay. And what is finally the probability of clubs? Out of 50, 24%. They sum to 100% because of the 50 outcomes, they're all accounted for. They're all accounted for in that little table. Okay, you're doing something similar to this in your quiz for Thursday. So very similar. I think you're rolling. Are you rolling a die again? I forget which one. It's a tablet.
Oh, yeah.
Is it rolling a die?
It's the
Oh,
wheel.
it's the spinning the wheel, right? Which
Zero to nine- zero.
essentially they're all the same experiment. This is a 4-sided die. Your quiz is a 10-sided die. That one over there is a 12-sided die. In class was a 6-sided die. A coin is a 2-sided die. They're all dice. They're all dice because they all have equal likely probabilities. Cheryl, go ahead.
What's a fat kid Josh?
Do you know what a ball pike is? So those big exercise balls, those like yoga balls.
Yeah.
I sit on one on my office because it's good for your core.
Theoretical.
A pike on one of those. I call it a pike. I'm sure if this is correct. You put your you get like a push up with your feet up on it. Then you pull the ball towards you and you pike your body up.
Oh, wow.
A fat kid Josh is a pike followed by then letting your feet go to one side and the other. So you get the core on the front, but then you get the core on the left and the right. Usually screaming by the time you're done.
So you're not pulling your legs in, you're just...
You do the pike, and then you follow that once you're up by letting your legs go from one side to the other. So you're rolling the ball side to side.
Okay.
Yeah, I'm glad we didn't get a roller flush on those because I would have beat
See,
myself.
I'm not the only one that wanted to know.
Yeah, fat kid Josh. What the hell is a fat kid Josh, right? We've got all these things, all these exercises, the Onos, the fat kid Joshes. Yeah, there's the partner pull-ups, kind of PG. So yeah, fun stuff.
I just heard of a dirty hippie yesterday. I like that. The names people come
Dirty
up with.
hippie, yes.
But it's a drink. It's not an...
Oh, they talk about me. I get that one too sometimes. What? Yes. Okay, cool. So now we're down. I think we're somewhere. Hang on. Let's figure out what the hell we're doing now. We got that. Percent error. Here we go. Percent error. That's what we were trying to work on. Okay, so now we're knocking the percent error for the experimental probabilities found in exercise 25. Okay. So I'm going to swing over here to this sideboard, and we're going to do this. All right. So this is E3. Yeah, E3. Okay. Fair enough? Okay. So we've got let's see. Let's keep track of what we did in class. We'll do outcome. And we've got diamonds or hearts. We've got diamonds. We've got, what the hell? It's drawn again. It's pretty. Hearts. Diamonds. Spades. And clubs. Yes, right over there. And then we've got the observed. We've got the observed. And we've got the theoretical, and then we've got the percent error. We've got the percent error. Let's keep all this, keep track of all this here. Okay, so we can go a little good. So, experimental probabilities of hearts was 34%. For diamonds, 16%. Clubs, 26%. Clubs, another spades, excuse me, spades 26, clubs 24%. Fair enough so far? Mm-hmm. Okay. Theoretical, for all of them was 25%. We were expecting 25% for all of them. Do you remember how to do percent error? Remind me.
Observe
Go ahead, Cindy, help me.
Observe minus theoretical.
Good, over
True value.
Good, over your theoretical. So you're expecting this as a base, and then you're looking at the distance between this and this. So you've got 34% minus 25% over 25%. 16% minus 25% over 25, and so forth and so on. 26 minus 25 over 25, and 24 minus 25 over 25. Make sure we can all see that. Now, what's slick about using 25%, it's actually pretty easy to calculate the error without using a calculator, without having to use a calculator. So, what's 34 minus 25? 9. That's 9. So you've got 9 over 25, right? Which is the same as 36 over 100, which would be 36% error. Positive 36% error, wouldn't it? Right, yeah.
Or if you set this up a little different and I put in the observed, I put in those numbers right then.
So instead of using the probabilities, you use the counts.
Yeah, that's
Yes.
Okay.
Yes, check this out. Can we go back to that, Matt, if you don't mind?
That's fine.
I want to come back to Matt's question. He asked a fantastic one on a mixed sheet. I don't know if you guys heard it or not. I want to rephrase it. Let's just knock it out this way and finish it this way, and then we'll see how everything pans out.
You already hit all my questions, so they don't even have to.
No. I want to know why it doesn't matter how you approach it.
Okay.
You're correct in saying that you don't have to, but there's a mathematical reason. I want to make sure it's clear.
Okay.
That's to why. Okay? How about 16 minus 25? What's that, guy? That's negative 9, isn't it?
Yes.
So this is going to be negative 9 over 25, which is negative 36 over 100. So they cancel. That's nice. 26 minus 25 is 1 over 25, which is 4%. And guess what that is? Yep, has to be, doesn't it? Has to be negative 4. Has to be negative 4. They sum to 0. Does that surprise anyone?
No.
No, because they have to sum to 0. Over time, they're going to balance out, but they have to sum to 0 because you have 50 observations here and 50 observations here. You're essentially subtracting the 50 and the 50, which over time will each of the individual ones will become closer to 0 over time, for sure. Matt asked a fantastic question. His question was, I didn't use the percentages. Like, I didn't call this 34%. He called this 17, because that's how many